In other cases, the wave itself is easier to see than the individual oscillators. Perhaps more surprising, waves propagate not only along the surface of water, but even through the interior of a crystalline solid. A disturbance's speed depends on the medium through which it passes, and on the connection between one bit of matter and the next. If the linkage is weak, the disturbance passes slowly. If it's strong, the disturbance travels rapidly. But no matter the speed or the medium, water, air, or even a solid, all waves that propagate through any medium are called mechanical waves. Mechanical waves, or impulses, pass through a crystal from atom to atom because each atom is bound to an equilibrium position by electrical forces. When disturbed, they act mechanically, exactly like masses connected by springs. When an impulse moves through a system, no single oscillator goes very far, but the disturbance moves right along. Sometimes mechanical oscillations can be more moving than disturbing. It can be art as well as science, and it can be enjoyed as both. Musical instruments send continuous waves through the air that can be visualized as well as heard. Masses connected by springs may not look like beautiful music, but the principle is the same. And it can be described using a few handy terms. Each wave has an amplitude, the size of the disturbance, which is preserved as the wave moves along. It also has a definite time for each complete cycle, called the period. The inverse of the period is called the frequency. The tone of music depends on its frequency. The higher the frequency, the higher the tone or pitch of the sound. And the loudness of music depends on the amplitude. But no matter how loud, sounds are always on the move. And regardless of pitch or loudness, all sound travels through the air at exactly the same speed. If it didn't, every listener would hear a different performance. Whether it's short and sweet or loud and long, every wave has a definite distance from one compression to the next, called the wavelength. The wavelength equals the period times the speed of the wave. Or in other words, frequency times wavelength equals speed. Lower frequency generates a longer wavelength, but the speed remains the same. For sound waves in air, the speed is always the same, regardless of the frequency, the wavelength, or even the amplitude. But in this world, all waves don't get an even break. Sound and water waves travel at different speeds. And unlike sound waves, water waves can travel at speeds different from each other. At a considerable distance from a continent, way out there in the deep blue sea, long waves travel faster than short ones. But closer to the shore, waves travel together. And no matter their length, all waves decrease in speed as they approach the shore. In the mechanics of waves, that's the long and the short of it. Because on land, or at sea, in fact anywhere at all mechanical waves follow the same basic principles. Wherever anything makes waves, harmonic oscillators respond and then spring back. The oscillators are linked in such a way that every cycle of one excites the oscillator beside it. But what determines how fast the wave moves?
For masses connected by springs, the speed of the wave depends on the stiffness of the spring, the mass of each oscillator, and the equilibrium distance between them. In water, gravity is the force that makes the water spring back. That's why gravity determines the speed at which a water wave travels. But so too does the length of the wave itself. If the water is much deeper than the wavelength, the wave speed is approximately equal to the square root of g, the acceleration of gravity, times the wavelength, divided by 2 pi.
In other words, long ocean waves move rapidly, while short ripples move more slowly. The result is that in deep water, long waves pass right under the surface ripples. And whether they're long waves or ripples, water waves differ from simple mechanical ones in some other ways. For example, masses in springs can oscillate along the direction that connects them. These are called longitudinal waves. And they can also be made to wave sideways. These are called transverse waves. But water waves are neither longitudinal nor transverse. Instead, each bit of water on the surface moves around in a little circle, each circle slightly offset from the next, altogether giving the familiar undulation of the watery surface. As a water wave approaches the shore, it comes into ever-increasing contact with the seabed, which slows it down. The closer the surface is to the bottom, the slower the wave. In shallow water, the wave speed is approximately equal to the square root of the acceleration of gravity times the depth of the water. When this happens, the thick part of the wave moves faster than the thin part, spoiling its sine wave form. and ultimately causing the wave to break.